直接就进到，不用签那种，应该是
就等下点开始之后再看看它信息。
Hello, good afternoon. Welcome to fifth round of this competition. Before the beginning of the competition, I would like to introduce our jury committees. I'm Yi from Taiwan Tech, and Professor Mo from National Tsinghua University. Professor Hu from National Taiwan Normal University. And Professor Xi from National Taiwan University. And Professor Xie from National Now, please, for each captain, please introduce your team.
I'm Captain from Variable 1. I'm Yang Youyi, Yan Yutong, Chen Shenci, Chen Youqi, Hou Wenxin.
I'm the captain from the team miracle. I'm Huang Yuchen. He is Ling Qian. He is Luo Zichun, and he is Wu Zhengtang.
I'm the captain from Team Selfie, and we are from Concordia Middle School. And I am Chen Xiaochen. This is Li Yiling. This is Liu Xingyu. This is Chua Yaju. This is Elizabeth.
Thank you for your participation. And since this is a fifth stage, so we don't have challenge. So our problem would be problem 9, magnetic assist. So perhaps it's time to prepare your presentation. Also, reporter, opponent, and reviewer, please write down your name on the blackboard. Thank you. Stage is yours.
Honorable juries and fellow competitors, I am the reporter from Team Excelsior. For today, I'll be reporting problem number 9, magnetic assist. The problem statement reads, attach one or two magnets to a non-magnetic and non-conductive base, such that they attract the magnets suspended from a spring. Investigate how the motion of the moving magnet depends on relevant parameters. For today, we'll be mainly focusing on 1. Different kinds of motion of the pendulum, and 2. Energy transformation during the whole process, and 3. How relevant parameters will affect the pendulum. This is the outline of my report. We'll first talk about the phenomenon, then we'll talk about the theoretical model, we'll talk about the experiment when it's one magnet only, and we'll have the discussion. And here we'll talk about with multiple magnets, and we'll finally have our conclusion. First is the phenomenon. This is our experimental setup. As we can see, we have 2 observation videos that show both the swing mode and the conical mode. We have a fixed horizontal base so that the string will be suspended vertically. And the string we used is a light string and is a fixed length with a thin straw so that it won't have any deviations. And of course, there are 2 neodymium magnets. And of course, we use an aluminum extrusion to ensure the stability of our experiments. First, we'll talk about the qualitative explanation through a force analysis. So, to remain at the same height, the centripetal force has to maintain these 2 equations. And when we can see that when theta angle is large enough, the magnetic force can be ignored. And we can also see that L cosine theta phi dot squared will remain a constant at this height. And without energy dissipation, the whole system obeys the law of conservation of angular momentum. And it can also be noted that when angle theta decreases, the magnetic force increases because the distance between the 2 magnets are decreasing. Next, we'll talk about the qualitative explanation through energy perspective. The first condition is when there are bigger degrees of theta. And in this condition, the energy transformation will mainly happen between 2 kinds of energy. First, it will happen between the kinetic energy and the gravitational potential energy, as you can see as shown. And in the second condition is when it has smaller degrees of theta. And in this kind of situation, the energy transformation mainly happens between 2 kinds of energy. It happens between the kinetic energy and the magnetic potential energy. It should also be noted that constant dissipation happens during the entire motion, which includes air drag and eddy current. Next, I'll be talking about my theoretical model. Sir? Okay, so first, to quantify the effect between magnets, we first have to find out their dipole moment each time. So, sorry. So first, to quantify the effect between magnets, we first have to measure the dipole moment. And to do this, we first use a Gauss meter to measure their dipole moment at each distance. And like this. So we first use the Gauss meter to measure their dipole moment at each distance. So by obtaining the dipole moment from each distance, we can draw it into a graph and fitting. And after fitting, we can find out their dipole moment. And then, of course, we use the Gauss meter to find out their dipole moment. And also, to talk about it more, we assume that our magnets are uniformly magnetized. And that's where we're talking about the equation of motion. And so we decided to use the Lagrange equation to solve the equation of motion. And we'll first talk about the magnetic potential energy. And since the system is radiosymmetric, only theta angle affects the magnetic potential energy. And the magnetic potential energy, the magnetic field that's provided from the bottom magnet can be provided here. And the magnetic potential energy can be found out afterwards, like this. And also, the vectors of the coordinate are provided over here. Next, after we run our numerical solution into our simulation and draw them into a graph, we find out that this is an energy well. And there is an energy well at the top of each magnet. And since the magnets have a tendency to go down to a lowest potential energy, we draw the wells like this. And this is a 1 magnet and 2 magnets graph of magnetic potential energy. Next, we'll talk about how we solve the equation of motion. So first, we can find out our kinetic energy like this. And first of all, we would like to define some of the variables. Theta angle is the angle that's between the tilting angle and the pendulum. And phi angle is the spinning angle of the horizontal plane. And through our calculations, we can find that kinetic energy it can be written like this. And also, gravitational potential energy and magnetic potential energy can be written in these following equations. And finally, Lagrangian equals kinetic energy minus potential energy. So after all this, we can run our numerical solution in collaboratory to solve the equation of motion for our problem. And before we run our numerical solution and run our equation of motion, we first have to consider the effect of damping. So we drew them into, and so this is the experiment we used to consider the damping effect. And through fitting an exponential equation, we can find out that the damping beta constant is approximately 0.05821. And after that, we can finally run our numerical solution in Spider. And after we run our numerical solution, we can put our simulation through VPython. And as we can see, these are the simulations of the conical mode and the swinging mode. And we can also see that variables are provided over here. Next, I'll be talking about my experiment when using 1 magnet. So we first define the time over here. And we can see that the amplitude of our experiment and our theory matches. It's almost the same. And also, we can see that the amplitude of these two, experiment and theory, has an exponential decay, which fits our experiment and theory. And also, we can divide this into 2 phases. When it has a larger theta degree, it acts like a simple pendulum because the magnets have a lower effect. But it has a smaller theta, the base magnet, and has the equivalent gravitational field. So it will attract the magnet more. And at the bottom corner, we can see the different pendulum lengths, the time of different pendulum lengths. And we can see that when you have a longer pendulum, the duration it would have to take for you to stop is longer. And we can also see that no matter which kind of pendulum length you choose, it will all have a decay over time. Next, we'll talk about the 3D pendulum length. And because, as we previously mentioned, to remain at a steady height, L cosine theta 5 dot squared has to remain as a constant. So when decreasing the theta angle, the pendulum length decreases. And in this situation, the potential energy is changing to the kinetic energy. However, when we have a longer pendulum length, we have an increasing theta, angle theta, which will store kinetic energy to potential energy. And no matter what kind of pendulum length, in the end, acceleration due to attraction to a base magnet will always happen. And over here, we can see that with a longer pendulum length, it will have a longer duration to finish its motion. So it fits our experiment and theory. Next is discussion. And we first discussed about the multiple magnets, and we put it into our our system, and we found out that the differential equation is too complicated that the collapsed environment actually died. So we had to simplify the magnetic potential energy. And before it looks like this, it's very complicated. And afterwards, we suppose that that the magnetic potential energy has a negative correlation between the magnetic strength. And after fitting, the collapsed environment said, I can handle this. So this is a simplified magnetic potential energy well, and we find out that the approximation gives a simpler but accurate method for the simulation, so the modification is acceptable. And next we'll talk about the equilibrium points. So the pendulum must stop at stopped at one of these points. It's 0.1 or 0.2 of the magnet, which is the stable equilibrium. However, the saddle point is an unstable equilibrium. It's at the middle over here. And we first have to compare our experiment with our theory. So in the right hand side, the graph shows that when at different colors, the different initial conditions and the different ending positions. And we can see the ending point finally ends at 0.2, and the trajectory can be shown over here. So we want to prove that our system is really chaotic. So we have to find out how sensitive to initial conditions the system is. So we magnitude it once again, and again, and again. And we find out that at approximately 0.5 millimeters, under such a short distance, the little difference in initial conditions significantly affects the result. So we can find out that it's really chaotic. And of course, this is our result, and with a smaller damping coefficient, it's a stronger chaoticity behavior. Conclusion, the energy transformation happens during the whole process are the energy transformation between kinetic energy and potential energy, and with bigger and smaller degrees of theta. And the pendulum will move as such, and I previously mentioned in my report. And thank you.
Thank you for your presentation. And my first question is, the angular momentum is all conserved in your experiment?
Could you please rephrase your question?
Okay, so is the angular momentum conserved in your experiment?
The angular momentum
Yes.
is what?
It's almost the same.
Yes, we consider yes.
And how can you define the smaller angle in page 8?
Smaller angle. It's approximately 10 degrees
Okay,
theta.
thank you. And the next question is, you talk about transfer.
Yes.
And energy transfer is almost 100 transfer. It's 100 transfer.
It's not 100 transfer. There will always be some kind of energy losses,
Okay,
dissipation.
thank you. And the next question is, how can you measure the energy? Because you analyze the energy in your experiment. And
This is through our theoretical model. We can find out
so
that.
is that your simulation, right?
Yes, but it fits our experiment as well.
So did you have data about energy?
Well, energy can really be like.
Yes, because you talk about energy, but you don't have data about it. So
We're talking about like the transformation of energy.
Okay, so next question is, why do you use 2D to describe, not use 3D to describe?
And at 2D, we're talking about a swing mode. And at 3D, we're discussing about like a 3D conical mode. It's like a conical pendulum.
You should use 3D because in your simulation there's 3D.
But because we talked about 2D because we didn't give an extra tangential arbitrary force.
So next question is, which theory did you use? Some laws of
The chaotic theory was provided in our report.
But is there any other theory? Because not just chaotic.
We use our experiments to define the equation of motion.
Have you considered damping about it?
Yes, we did. We mentioned it in our report.
Okay, thanks. Please prepare your speech, follow-up discussion.
就是那个有很多系数，就是以前的那个，它那个分盘系数的又跟它的 phase function 不是一样的，应该没有，后悔我没有拿。 Hello everyone, I'm opponent from variable 1, and today I would like to oppose number 9, magnetic assist. So here's first statement. Attach one or two magnets to a non-magnetic and non-conductive base such that they attract a magnetic substance from a string. Investigate how the motion of the moving magnet depends on relevant parameter. So I think the main focus might be the different kinds of motion of the pendulum and energy transfer. And next one is observation is cognition mode and swing mode, because they have short length. And their theory, they use force analysis and conservation of angular momentum. But I don't think the angular momentum will be constant in the whole experiment. And energy transfer between kinetic energy and potential energy also influenced by air drag and other things. And magnetic potential energy and reactive only the theta affect the system. And the energy well, equation of motion and damping. And they also consider about the chaotic. And the measurement is dipole moments and measure damping ratio and coefficient, but didn't use in the energy loss discussion. And experiment, vary pendulum length and angular velocity is these are their independent variables. And they use Python to simulate cognition mode and swinging mode, and simplify the simulation system so the system didn't crash. So here's the discussion point. The first one is definition of condition, because the reporter didn't mention the initial condition and the boundary condition when the chaotic system starts. And the next question is the setup. I will ask the setup because they didn't show us the length between other things. And the next one is the center of the magnet, because I think the magnet field will be different because the magnet is not just a point mass, and the results of trapped in different numbers of magnets. And chaotic system is also depends on definitions of chaos. And simple pendulum, because I saw the period, the formula of the period formula in their presentation, and boundary condition in the chaotic mode. So I think the most important thing is chaotic system, because they didn't combine this one to the data. So this will be the first one. And the simple harmonic motion is also the things I want to discuss. So now I would like to invite the reporter on the stage. So the first one I would like to ask about the chaotic system. So could you please continue?
So we would first like to define our chaotic system as how sensitive to the initial conditions our system is. But the definition of chaos is by varying the initial condition, the outcome and process of our experiment will be different. Yes,
So please enter the data about chaotic, because you analyze the chaotic, but could you please explain when the chaotic system begin? It's throughout the whole experiment, or it's just
Okay, so as we can see over here, under such a short distance, only 0.5 millimeters little difference in initial condition significantly affects the result. So because the initial condition is different, it will change the entire outcome and process of the experiment. So chaotic system occurs throughout our experiments, and we didn't specifically talk about it to compare.
So I want to ask if this one is chaotic system or is just an environmental factor to cause this one. Can you prove that?
This is definitely a chaotic system because okay, so this this graph over here shows. So for example, if our original system is original initial condition is at orange, it will eventually lay on 0.2.
Okay, so I understand, but I want to ask, what is your boundary condition?
Could the opponent specify like that?
It's a boundary condition because every chaotic system has its own boundary condition. So what is your boundary condition?
Do you mean in which condition will chaos happen?
Yeah, it's
Okay.
boundary condition, and because you say that chaotic systems throughout the whole experiment, then what is your boundary condition?
Okay, so my boundary condition is our boundary condition is when we have a different initial position, then chaos system will occur. So that is our boundary.
But I don't think the chaotic system, this one is chaotic system because I think I agree that it's chaotic system, but I think this one is not a boundary condition because the boundary condition should be definite and sure, not just use this to mention. Do you agree with me? Not just this one to explain. Do you agree with me?
Yes. Yeah. We
Okay,
agree.
so-
We agree. We should specify on the
Okay,
boundary condition.
so let's go to the next stage. It's because you use the simple harmonic motion in your theory.
I didn't mention about that.
But I saw T in period.
For the pendulum name.
Yeah. Because this one, I think, because we all know this one is the simple harmonic motion formula about the period. So why do you use this one?
Well, we use this equation to show that because especially we have the equivalent gravitational field, we want to use this formula to express how the time period will be different in different phases.
So I think that this period will be different because your angle is not small. It's not
Yes.
too small. Fix this.
It will be different because as you can see, the amplitude experiences exponential decay, and this is our time over here, and we have a graph that shows
But there's also some.
decay.
Okay, sorry, but there's also some difference between your. Is this one your theoretical data?
No, well, this is actually conducted from our experiments.
So this one's your data, and this one, what's this one?
As we can see over here, we marked that we have used a 12 centimeter pendulum length as our experiment, and we have a theory that the amplitude will experience exponential decay, and we found out that our data matches with our theory.
But I don't think this one is matched because there's also some error. Can you explain the error about that?
Well, of course there are errors because we did consider the energy dissipation, but the actual energy dissipation from our theory doesn't necessarily match with our actual experiment.
So have you
yes.
considered the energy loss about this one?
Yes, we did consider the energy loss, and we did find out that it's almost identical. But
Have you qualified that?
can we qualify the energy loss?
Yes.
Yes, we quantified it.
It's
Quantified.
yes, it's percent. It's maybe your loss 5% energy.
Oh yes. So
Calculate that.
back to our. Okay, so this is what we're talking about when we talk about energy loss. So it's basically exponential damping, and we found out that our constant beta is 0.05821. So that's what we brought to our experiments.
I agree with damping coefficient, but I didn't see you use this one in your fixed function. So could
Yes,
you please show me that?
we didn't show it, but we applied this
So could you please
number.
show me this one in your theory, or because I didn't see you use this value in your
Yeah,
function.
we use this for both. Actually, we test out the exponential equation for the damping based constant, and then this is what we found out after our experiments, and we applied the damping beta constant to our theories.
So you do the simulation about this one. Simulation.
Yes.
So
And also,
could you
but
please show me the code about your simulation?
it's over here.
It's code, not this one. It's
Okay,
simulation
yeah.
code. Because you say you use Python, right?
Here. I think I included it in my here.
So please explain your code.
Okay, so we first use the Lagrangian equation.
Yeah.
So that means kinetic energy minus potential energy, and we coded it with the numerical solution that we ran with Spider. And because we have to consider damping, so this is the outcome for our simulation, and it considered beta, but it considered the damping beta constant.
Okay. So, but I also think there is some parameter you lost consider because you say you consider chaotic system. So is the simulation is also fix your chaotic system.
Yes.
Why? Can you show me?
Because we considered the.
So you lost. So
No, we matched our simulation with our experiment, and because we know that our experiment experienced chaotic system, so we can therefore understand that our simulation matches with our
So
experiment.
did you have experiment? Did you have function about chaotic system and your damping coefficient?
So we changed. So by changing maybe like a small initial condition of our theory, we can find out that it matches with our experiment. So if we change a little bit of the initial condition, even at we previously mentioned just 0.5
But you
millimeters,
still didn't show me the equation about that. So
it's part of our simulation.
Okay, so I understand, but I disagree. So next step, please. So did you compare your 2D mode with real world? Because you say
Yes.
because you say you use because there's 3D in real world, but is there because
So we define 2D is when we just release the magnetic pendulum without applying an arbitrary tangential velocity.
but I think the pendulum may be like this one, not just this one.
Yes,
Not
and
just
so we did experiments to describe both situations.
So can you theory to prove that? Can you theory to show me why you can just use 2D, not use 3D?
Oh, because as our
Do you have equation about that function? So
I think we did.
okay, so next question. So what's the difference between single pendulum and this one and your system? Have you compared these two?
Yes. So here.
Because you say this one is single pendulum formula.
So we didn't show the graph of it, but we did actually find out that when the theta angle is larger, it acts like a simple pendulum because it doesn't have the attraction force between the magnets doesn't occur that much. So we did compare our experiment data with actual simple pendulum.
But I think you should have a fixed function about the period because you use this one and this one is the single pendulum. But I still think you should have.
The reporter agrees with the opponent that he should provide a comparison between a simple pendulum and our
Okay, so next question. I want to ask about your setup.
Okay. So
So have you did the experiment with just one magnet?
yes.
Okay, so please show me the setup. Maybe the previous one. Yes.
Here.
So what is the distance?
Okay. So the distance between the horizontal plane, the aluminum extrusions, this is I think
So
39.7 centimeters.
So do you think this one is the same or is different?
Oh,
These two distance is the same or different?
No, and we didn't consider the two distances because we only considered if the magnet is directly on top of the bottom magnet when it's at static equilibrium.
So I would like to summarize the discussion. The first one is chaotic system. We agree with reporter that chaos is sensitive to the initial condition. But reporter has had boundary definition because I didn't see any boundary definition in their presentation, and we didn't know it is experiment error or chaotic speaking. Just because they didn't consider environmental factor and they just say it's chaotic, but chaotic system. But I'm not sure. We think initial position is the initial condition, but it's not the boundary condition. And the next one is simple harmonic motion in simple pendulum period. The result didn't completely match the theory. Reporters think energy loss didn't matter. And damping used in simulation to simulate the environmental with damping, but in simulation we can't know the damping effect in the environmental of chaotic system. So that's all. Thank you.
First, I want to ask some questions about the report printer 2K6. You have mentioned that when theta is large enough, you can ignore the magnet force. So what is the exact boundary of the condition? Like how big the theta will become, and then you can ignore it.
Okay, so I think around as a picture is around 45 degrees when we can
Well, but the picture is so
it's not accurate, but
okay.
through our experiment we found it's basically
Then
around.
how about the theory? How big the theta will be that can ignore the magnetic in your theory?
We used our experimental data to match our theory. So the same.
Okay, next question. And in page 24, you talk about the chaotic, and because you didn't put your experiment setup on about the chaotic, so I don't know that you only simulate the phenomenon, or you actually did the chaotic experiment. Like this is from your experiment or the simulation.
Okay, so this graph shows the definition of chaotic system, and our experiment matches the graph.
So this graph is simulate.
Yes,
The simulation.
Yes.
Okay, then that's all. And next, I want to ask about both the reporter and the opponent. First, did you consider the magnet force of Earth?
We considered it, but because it's 0.5 minimal Tesla, so it doesn't need to be considered.
It's neglectable, right?
Yes, it's neglectable.
How about you?
So your question is have the reporter consider the magnetic?
Do you think the magnetic force is important in this experiment?
I think in problem statement they say it's all attract. So this one is if they attract.
So yes or no?
It's okay. Yes, it's yes.
So and that is important.
Is that important? I think it's yes.
Okay, yes. And the next question is that in the two magnet experiments, you have mentioned that the final magnet will stop at 3 points. Do you know what I'm talking about?
Yes.
And how about the one magnet experiment? Will it always stops at the right top of the
Yes,
base?
it will.
You think it will?
It will.
Okay.
I think sometimes it will rotate, so it will not all the same.
Okay. And the third question is that what is the most important parameters for one magnet according to different theta? You mentioned that before. Okay. This question is about the opponent.
So we think it's initial condition because
What initial condition?
Because
Like gravitational force or magnet force?
position of magnet.
Hello, I'm Ian from Team Miracle, and today I'm the reviewer of the magnetic assist. And first, I want to, here is the problem recap. First, this is the problem recap, and the key points are they are focusing on different kinds of motion, the energy transformation, and what factors influence the magnetic motion. And the summary of the reporter and observation is the setup of swinging mode and control mode, and the swinging mode for 2D and the control mode for 3D. And a qualitative explanation of motion equation and energy transformation of K and B. And in the theory, they talk about magnetic potential energy well and Euler-Lagrange equation and the measurement of damping effect, and also some numerical solution. And at last, they use the angular momentum conservation. And in the experiment, they mentioned that larger theta has simple pendulum, and smaller theta will cause longer length has bigger phi. And they also proved the chaotic, and they use simulation about the chaotic. And the things that reporter did great on is that they do multiple parameters and they explain the theory clearly and detailed. And they have smooth presentation, and the experiment I think they did well on. And the cons are there are lack of photos to show the experiment setup, and they use simulation rather than experiments for the chaotics. And here's the overall opponent. They point out the missing parameters that the reporter didn't mention. They also point out, they also talk about the chaotics and the theory that they can explain. But I think the opponent is too focused on the chaotic system that there are some other parameters they didn't talk about it. The key discussion of the definition of chaotics, and the opponent said that this should be definite and short, and we think that they should be defined it quantitatively. The graph of 2D pendulum length, the opponent say that you can explain the deviation on the graph. The reporter applied damping in the simulation. And the third of the key discussion is the comparison between 2D and real world. And the opponent mentioned that no theory to prove they can be similar to 2D. And the reporter said that we use experiment to know that. Next, I want to went into our question. I asked the reporter that when theta is large enough, the magnetic force can be ignored, but they just said that they use their experiment to know the boundary of the theta, but not in their theory. And about the chaotic, the reporter only simulate the phenomenon, but not do the real experiment. And I asked about the magnet force of Earth. The reporter says that they think this is neglectable, and the opponent doesn't agree with this, but I agree with the reporter, and I agree with.
Okay, thank you. Now, so let's please conclude.
So now I would like to give our concluding remarks. First, we would like to have a definition of our chaos system. And for that, we have defined it as the system is very sensitive to the initial condition. And we can also acknowledge that chaos occurs when the initial condition is different. And our boundary condition in the chaos mode is when a different initial condition is the boundary. However, we do acknowledge with an opponent that we should specify on the exact boundary conditions. And for number 3, we did consider the energy dissipation in our theory, and we did measure the damping beta constant through our experiments, so we can fit it into our theory and experiments. And number 4, our simulation matches with our experimental data, and so yeah. And for number 5, we defined a 2D swinging mode when we didn't provide an arbitrary tangential velocity. And through observing the experiment and simulation, we found that it only acts in a 2D world. And the 3D conical mode is when we provided the velocity. And when we don't provide the velocity, it will act as a swing mode, like a pendulum, and it won't affect the 3D world. And for number 6, we didn't consider the distance between 2 aluminum extrusions, but we did ensure the magnets will be directly on top of the bottom magnet to avoid any deviations. So we didn't have to consider the distance between the 2 aluminum extrusions. And for number 7, regarding to the reviewer, the magnet will always stop on the top of the center when there is only one magnet, and it will stop on the top of the magnet when there are 2 magnets as well. But there's some conditions when it will stop at the middle, but it's nearly impossible. And that is the end of our concluding remarks. Thank you.
Okay, thank you. Now, a question from the viewers.
A little bit confused. I have a question for the opponent first. When you mentioned this boundary condition, I don't really know exactly what you mean by the boundary condition. Secondly, I don't know why in your summary you are saying this angular momentum is not conserved, but you didn't change this problem asking you the reporter. Why is that?
Firstly, I would like to talk about the angular momentum. That's my mistake because I forgot to discuss with him. And the next one is chaotic system. I talk about boundary condition.
So angular momentum conservation is not a problem.
I think the angular momentum is not constant in the experiment.
Yeah, but then my question then about this point, why don't you in the discussion asking the reporter?
That's my
That's
mistake.
my question. Yeah.
That's my mistake because
Okay.
I'm focused on chaos.
Okay. And what are the boundary conditions when you say that?
I think the reporter should consider the boundary condition because boundary condition begins when the system becomes irregular and unpredictable.
Yeah. My question is, what do you mean by boundary condition?
It's when it stops.
Boundary condition is problem.
So the condition that made the system chaos.
The condition of what?
It's when the experiment stops and
So that's the initial condition of boundary condition.
Initial condition is the first, but when initial condition is before experiment and boundary condition is after experiment and the chaos starts.
Okay, anyway, but since before you also answer the boundary condition, what do you mean by your boundary condition?
Actually, we're not really sure. So maybe we thought that the opponent might have mentioned about like the differences in the initial condition as a very good. I mean, we mean as like how different of an initial condition it has to be before it turns to like a chaos system.
And also, then you didn't respond at all. I mean, when
Because
the angular momentum conservation, I don't know why you didn't respond this part.
Because the opponent didn't really talk about it afterwards in the discussion, so we focused on what she discussed about. So
I mean, even in the summary, you didn't respond at all. So that's my just anyway, yeah. And also the same question for the view having these two parts. I didn't see any clear indication. You have anything to say about this for these two parts?
Oh, sorry, but I was focused on the question that.
Okay. Okay. Anyway, yeah, I'm done.
Any question from the jury?
Can you tell me the definition of the chaos?
I think the definition of chaos is when the system is begin irregular and unpredictable, but I think it's very high sensitive to the initial condition, and also it is regular, but it's in some parts it's irregular, so we cannot totally ensure that.
So I think there's a relation between the damping that you just mentioned.
So the definition of chaos would be when changing the initial condition, the outcome and the process of the experiment will be different.
Then why you always ask him to do the simulation? Because you already say it is unpredictable.
So
I said, you already say that with this in the chaos system, it is unpredictable. Then why you always ask him to do the simulation on the chaos system?
because they discussed about that, and they did, yes, I saw they did simulation.
They do simulation because they want to prove in what, even for the small distance, then the behavior is completely different.
I asked him because I don't know that if he didn't do the experiment, I don't know whether the simulation is correct or not, I think.
So you focus on the chaos. In your experiment, I think even the spin of the magnet or the size of the magnet even influence the motion independent. So you think in your experiment didn't control it from it, you think that your motion will be into the chaos condition.
So we control the like the jury mentioned, the size of the magnets for our experiments, and we also we thought it was chaos because the release point mainly. Well, we considered the release point to be different for initial conditions. The difference.
So you also think if you didn't consider the spin
we didn't really observe the oscillation of the magnet when we conducted the experiment. So we didn't think of that we didn't think to provide that into our chaos theory. However, we do because we didn't spin the magnet before we released it. So we believe that it will be controlled. However, we do acknowledge that there could be some deviations, like air resistance making it spin. So we think that we didn't consider the spinning, and we didn't consider the original magnet because it's all the same.
So your theory or your model only consider the momentum or energy transition, but you ignore the real world parameters.
But we also did consider about like the initial conditions, and like we mentioned in our the graph that shows the blue and orange initial conditions.
So for opponent, you also consider chaos is very important thing.
I think chaos is important.
Okay, so for experiment part, you don't think the control of the experiments is do you think the control of the experiment is?
Sorry, could you please explain again?
Your experiment setup is this important or?
I think the setup is important because when we have to quantify the data, and we should use the distance in setup in the experiment.
So do you think maybe I say the spin of the magnet or the size?
I think that should be considered.
So how about the?
Yes, of course, the setup is.
So you also think the chaos is also important in this system?
You want me to compare the setup and the chaos?
For example, maybe the definition of the chaos in
What caused the chaos?
Yeah.
Yes, I think the setup will also cause the chaos.
Okay, thank you very much. Now, I think it's scoring time. Set. Okay, so for the reporter, 7, 6, 9, 5, 8. For the opponent, 6, 4, 7, 6, 8. And finally for the reviewer, 6, 6, 6, 7, 6. So any comments from the group? If no, then we conclude this stage and we can have about 10 minutes break. Please come back by 10 after 8. 3.